My dear friends, welcome to Rajashekar classes on Applied Data Science with Python. This is lecture number 526. In this lecture, we will try to understand logistic regression revisited, since we have seen how to solve constraint optimization problem. Let's revisit our logistic regression. How does logistic regression optimization problem look like? W star equal to argmin of logistic loss plus lambda into W transpose W. Isn't it? This lambda into W transpose W, this part, this one, lambda into W transpose W is the regularization, and this is the general form. Which one? This entire thing is general form, isn't it? This is the general form of our logistic regression. This one is logistic loss. This one is logistic loss over all the training points. So if you think logistic loss over all the training points, so if you think about it, I will try to give an interpretation wherein your regularization lambda into W transpose W would exactly similar to your Lagrange's multipliers. I will repeat. Let me repeat this point. I will try to give an interpretation wherein your regularization lambda into W transpose W would be exactly similar to your Lagrange's multipliers. Let me try to connect these two dots. Yes, let me try to connect these two dots on how regularization is similar to Lagrange's multipliers in some way. So what is our actual problem? What is actual problem in logistic regression? Our actual problem is find W star which minimizes your logistic loss such that W is normal to hyperplane. When W is normal to hyperplane, we assume that W is also a unit vector. W star equal to argmin of logistic loss such that W transpose W equal to 1. So if you see that this is constraint optimization problem, because we have an objective function that you are trying to minimize, and here you have an equality constraint. What is equality constraint? W transpose W equal to 1. Now using Lagrange's multipliers, this point is important. Using Lagrange's multipliers, I can take this W transpose W equal to 1 into the objective function as follows. So if I have to solve this optimization problem, remember this is constraint optimization problem. How can I solve it? It's very simple. It's just Lagrange. It is very simple. I just use Lagrangian of this is Lagrangian is L equal to logistic loss minus lambda into 1 minus W transpose W. Since it is an equality constraint, I can write it as 1 minus W transpose W or W transpose W minus 1. Either of them is okay. So we choose 1 minus W transpose W, isn't it? Now, what is this? This is equal to, I can logistic loss minus lambda into 1 minus lambda plus lambda into W transpose W. So lambda is Lagrange multiplier. These two terms, if you look at it, these two terms are which terms? Logistic, these two terms. So lambda is Lagrange's multiplier. These two terms, if you look at it, these two terms are exactly same as what we wrote our actual optimization problem. Which terms? Logistic loss. Just compare this one. Just these two terms. Compare these two terms. This is logistic loss in Lagrangian. In W star also you have logistic loss. Here you have lambda into W transpose W. Here also these two terms. This term first. This is first term. I can say this is first term, this is second term. This one is similar to this one is similar to this, isn't it? I can say these two terms, if you look at it, these two terms are exactly same as what we wrote our actual optimization problem, W star equal to argmin of logistic loss plus lambda into double transpose W. Here lambda is Lagrange's multiplier. Regularization can be thought of as importing an equality constraint, and the solution of it is here through Lagrange's multipliers. I'm just connecting these dots here. One way to interpret regularization is through equality constraint W transpose W equal to 1 and Lagrange W transpose equality constraint W transpose W equal to 1 and Lagrange multipliers. This is just one way. Remember, in machine learning, what happens is a great concept is discovered typically when somebody comes up with a great concept. Even things like logistic regression, linear regression, the first person who comes with this concept probably has one interpretation of this concept. Then over time, lot of people from lot of areas, probably statistics, from statistics, from optimization, from applied maths, lot of people are looking at this. They have alternative interpretations of the same thing. That doesn't mean that original interpretation is incorrect. All of them are correct. It just gives you much richer flavor because you are interpreting in multiple ways. This is like literature. If you think about it, great pieces of literature have multiple interpretations. In machine learning, great concepts like regularization have multiple interpretations, one of them being the equality, one of them being the equality constraint, Lagrange's equality constraint and Lagrange based interpretation. I request all of you go through this lecture once or twice. If you have any difficulty, just keep a comment. In my next lecture, that is in lecture number 527, I will discuss about an important lecture where we will discuss about why L1 regularization creates sparsity. Thank you very much.